So example 12. Example 12 is going to give us some more functions that illustrate where a derivative fails to exist. But we've already kind of got some of that under our belt. So I'm just going to scroll right up here above 12 and just kind of start a list here. This is examples of where a function is not differentiable. And remember, a function is differentiable if the slope or the derivative exists at that point. So we've already seen a couple of them. The first example that we've seen was the vertical tangent line. That's the very first type we saw, the vertical tangent line. That one showed up on something like this. The square root of x at x equals 0. If you recall what that function looks like, it's part of the parabola, the half of the parabola on its side. Why did the derivative not exist at 0? Because the tangent line there is vertical, right? And at a vertical line, the slope is either infinity or negative infinity, which is not a number. Okay? So that's a vertical tangent line. The other one that we saw, let me see if I think we've come across it. Besides the piecewise functions, which are always kind of the exception to the rule, yeah, we saw right here. Yeah, remember? There we go. You can recognize when two slopes from either side are not merging into each other because there's a little snag in the graph or a sharp turn. So that'll be another visual indication that a function is not differentiable there. We'll say it a sharp turn. And then there's a consequence from up here. When we first talked about differentiability, it says it turns out being continuous at a point is a necessary condition for something to be differentiable. It's necessary, but it's not sufficient. So if a function has to be continuous to be differentiable, then what happens if it's not continuous? Yeah, then it's not differentiable. So it'll never be differentiable at any discontinuity. At any discontinuity. So we have holes, we have vertical asymptotes, and we have jumps. Those are the three main types. Okay, so now we're going to look at the example 12, and some of these will be a repeat, but some of them will be kind of new as well. If I ask you to find the derivative, f prime, of any absolute value function, now this is not Jumpman. Jumpman is absolute value over a function. They're both linear. This is just the absolute value function. This is going to be a transformation of your V for victory graph. The way that you answer derivative questions for any transformation of the V for victory graph, which is just the plain old absolute value of x, you're going to solve it graphically, okay? So here's what you're going to do. You're going to put your function in standard transformation form. So on the inside, if you factor out the 2, you can bring the 2 outside the absolute values as long as it stays positive. So there's the standard transformation form. What does the 2 do to any graph out front? It vertically stretches it by a factor of 2. And in this case, the +3 is very important. It moves the graph over to -3. Now, the number in front of the x right here, that's a very important number because if we drop the absolute values, it looks kind of like mx plus b. So 2 ends up being the m. It ends up being the slope. But because it's the V graph, it ends up being plus or minus the slope. And so if you know the graph opens up, the slope everywhere to the right of -3, in this case, is 2. And the slope everywhere to the left of that point is -2. So plus or minus the coefficient of x, that's always the slope on either side. So really all you got to know is, does it open up or down? Because if it opens down, then that'll be flipped. -3 then is the only place where the derivative fails to exist. So if I ask you what's f prime in -3, you'd be like, oh, there's a sharp turn. That's the visual manifestation of why it's not differentiable. The real reason is the slope is -2 from the left and +2 from the right, and -2 doesn't equal 2. But that shows up as a sharp turn. So this will be DNE. Now, if you don't want to graph it and you want to know where the vertex is, you can always take the thing inside of your absolute values and set it equal to 0. If you solve that, that'll give you the value of x where the derivative fails to exist. That's going to be the x-coordinate of the vertex. But I can also ask you questions like this. What is f prime of -256? Negative 2. Excellent. Yeah. The slope everywhere to the left of the vertex, negative 3, is going to be negative 2 because it's a line. It's the same everywhere to the left. And what would f prime of 100 be? Positive 2. Yeah, anything to the right of negative 3 is going to have a slope of 2. Now, here's the type of question I like to ask. I would just give you this function, and I would just ask you possibly what's f prime of 3. And you'd have to be careful, right? Because the reason I like this question is if you put it in a standard transformation form, you're like, oh, he's asking me f prime of 3. 3 is the value where the vertex is. I know there's a sharp turn there. I know this is D and E. But is that correct? No, it's negative 3 where the vertex is. So f prime of negative 3 is D and E. F prime of 3 is just what? 2, right. So now that you know that I'm evil like that and I could try to trick you, it's not going to be a trick anymore, right? You're going to catch it. So that's how you handle all absolute values. But this falls under the sharp turn thing again, and we've already cataloged that up above, so I'm not going to rewrite it. Okay, now moving on to B. B is going to be a new parent function, right? B and C are going to be new parent functions, so you're going to have to memorize them. The cube root of x is the inverse function of x cubed. So all you have to do to get the graph of an inverse of any function is reflected across the line y equals x. So here's what the cube root of x, also known as x to the 1/3, same thing, what it looks like. It kind of looks like arctangent. It comes in from the bottom, passes through the origin, and then leaves like that. It's an odd function. It has origin symmetry. If you rotate it 180 degrees, it looks the same. So it looks like arctangent, but it's not arctangent because this one does go down to negative infinity on the left and up to positive infinity on the right. But what's happening at the origin? If I take out my little surfer here, a tangent line, remember, is glancing off the curve. So when you draw it, it's surfing the curve from underneath. What happens to the tangent line right there at the origin? It becomes vertical, right. So this one is kind of tricky because the graph at 0 is connected, and it's connected smoothly, right? But still, the derivative doesn't exist because we have a vertical tangent line. So we've already seen vertical tangent lines, but here's one where the graph lives on either side, and it's still vertical. So this would be smoothly connected. It's like the one time where a smoothly connected graph is not differentiable. Now, if you're ever given a graph without the equation, you're going to be told that there's a vertical tangent line there. Because if you're not told that that's a vertical tangent, it's hard to say, is that an infinity slope or is that just 9 billion? It's really hard to distinguish between infinity and 9 billion, right? Really hard. So you would be told, you would be given a graph and it would say, the following graph has a vertical tangent at x equals whatever. And you're like, I wonder why they're telling you that. Oh, the derivative doesn't exist there. Got it. Okay, and then of course the derivative exists everywhere else to the left and right. The next one is x to the 2/3, which is basically this function squared. And when you take all these y values and square them, they're never negative anymore, and they become a little bit steeper. So here's what this graph looks like. You will recognize it from your youth, I believe. I'll draw it in gray. It looks like this and like that. Okay? This has shown up on many a student's artwork, right? When you draw your little seascape, you draw the waves, and then you drew the sun in the corner, and you did your rays either like long, short, long, short, long, short, long, short. Remember that? And then you filled in the sun with probably orange or something. But the sun was always cool, so he was wearing shades, right? It was a cool sun. You ever draw sunglasses on your sun? And then the finishing touch of any seascape from your youth was to do what? You draw the bird, like one or two of them, right? And one was bigger than the other, not because it was bigger, but because it was in the foreground. Ooh, depth perception on a 2D paper, okay? This right here is kind of a sharp turn. I wouldn't recommend anyone touching the point of that, but we call this one a cusp. A cusp is essentially a curvy sharp turn, whereas the one on the absolute value is just a straight line, straight line. So any kind of curvy sharp turn is going to be a cusp, and for the same reason, the derivative is going to fail to exist. Now, this fails to exist for a couple of reasons. Notice as we come in from the left, the slopes are negative, and as we come in from the right, the slopes are positive, becoming more so on either side. So no negative number is going to equal a positive number. But the other reason for this particular function is we also have a vertical tangent right there. It's also vertical. But even if it came in shallow like, a positive number and a negative number, those aren't going to be the same. Now, you didn't know it back in the day, but when you drew this little seascape, you were drawing a lot of things that were not differentiable, right? Because look at the crests on the waves. Those are like inverted cusps, not differentiable, not differentiable, not differentiable. And then maybe you got really, really bold on one of your seascapes and you went dun, 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 and you drew like a white-tipped shark or something. The fin on the tip of that shark, not differentiable. It's a cusp. It's another cusp. Sharp turn. I forgot to make my water blue. Sorry. There we go. Actually, I better do this. Every ocean has a little oil spill in it, right? There we go. There's my BP drawing. Some of y'all actually did y'all's sun rays like this, I was told. Some people asked for it like shaggy rays. Some people use just regular triangles like this. Oh yeah, squiggly lines. I remember. I tried that. I had that stage. Squiggly lines because it's like the mirage on the horizon, right? The radiating heat. Yeah, very good. So anyway, the seascape is full of things that aren't differentiable. And this one is supposed to have y-axis symmetry, by the way. Mine doesn't, but you get the idea. So x to the 1/3 vertical tangent, x to the 2/3 cusp. And then the last one here, we've already seen this type. I just threw them in here to kind of have a complete list. This is a transformation of the square root of x function, which we have already seen. For what it's worth, though, this would shift over 10, and when you put it in standard transformation form, it reflects across the y-axis. But there's another vertical tangent line right there. So this does now become essentially a comprehensive list of places where a derivative will fail to exist. Of course, if there's no graph at all at a certain place, the derivative is not going to exist either. So this is mainly for where the graph exists, but the derivative does not. Vertical tangent line, any sharp turn, I guess we can add cusp to that. That would fall kind of under the sharp turn. And now any discontinuity, whole, jump, or VA, including on piecewise functions. All right, so that leads us to this very important theorem, which is something we already know, but we'll state it formally here. If f is differentiable at x equals c, then it also has to be continuous. And here's what it looks like using logical equivalencies here. Big D stands for differentiability. Big C stands for continuity. The arrow means implies. So differentiability implies continuity. So why is that important to know that? Well, remember how being continuous is an important prerequisite for lots of theorems? Right now it's just the IVT, but we'll have the EVT and two different MVTs later on. All of them require the function to be continuous. So you might be given a question and it'll say the following function f of x is differentiable for all x. And you're like, differentiable? Oh, that means the derivative exists everywhere, but it also means that the function is what? Continuous everywhere. And so now you have access to those theorems. If a function is differentiable, it's continuous, and so all those theorems can be applied. So any statement is an if-then statement. This is if it's differentiable, then it's continuous. And for every statement that's true, there is another statement that's also true called the contrapositive. The contrapositive essentially flips the if and the then and negates it. So here's what it would look like. Not C implies not D. This is the symbol for NOT, not. This is something we already knew. If being continuous is a necessary prerequisite for differentiability, then if it's not continuous, it's not differentiable. No way, no how. Now, is this true? If it's continuous, does that mean it's differentiable? No, that's not necessarily true. So you can put a line through it like that. We just saw a bunch of examples on number 12 where the function was continuous at the point, but not differentiable. So the only thing that's true is if it is differentiable, it's going to be continuous, and therefore if it ain't continuous, it ain't differentiable. All right, so the last thing that I want to do here is example 13. I want you to determine if this function is differentiable. Well, notice that the pieces that we're using, 2x minus 1, 2x plus 1, they're both lines, right? They're both lines. What's the slope of both lines? 2, right? 2 is the slope because it's mx plus b. So what's the derivative of both pieces everywhere? 2, right? If the derivative is the slope and the slope's always 2, then would this function be differentiable if the slope is 2 everywhere?
No, it's not going to be continuous.
Very good. Yeah. I could draw a line that's a slope of 2, and then another line that's a slope of 2, and connect them together like that. But then if I take one of those pieces and I just raise it up, now the slope is 2 from the left and the slope is 2 from the right, but it's not going to be differentiable because it's not continuous. So remember, to be differentiable, it's not just are the slopes the same from both sides. It must first be continuous if it has a chance at being differentiable. So here's how we would do this. Moving forward, we're not going to be using the alternate form to determine if it's differentiable or not. The alternate form, remember, we did that up here on example 10. So I'm not going to do it down here. The alternate form would catch it, though. As long as you use f of -1 to be the same on both sides, the alternate form would catch the fact that even though the slopes are the same, it's not connected, so it's not going to be differentiable. But here's what we're going to be doing moving forward. You're going to have an ability to make a derivative pretty quickly using shortcut rules. So if I ever ask you if a piecewise function is differentiable at the point of exchange, the first thing you're going to do is check for continuity. What's the limit as x goes to -1 from the left of f? -3, yep. And that happens to also be f of -1, right? Because it's less than or equal to. What would be the limit as x goes to -1 from the right-hand side of f? -1. Okay? So here's what you say. Since -3 does not equal -1, f is not what? Can we go straight to that, though? No. You have to kind of string along the arguments. Yeah. F is not continuous at x equals -1. And so f is not differentiable at x equals 1 either, or x equals -1. Yeah, so as long as you string along that argument, it's not continuous there, therefore it's not differentiable there, you're good. That's as good as using the alternate form. I put that under the alternate form column. Let's move it over to the continuity argument. We have a little bit more time than I expected, so let's go ahead and do the alternate form, okay? The alternate form, the only way I'm going to expect you to do it is like on the quiz, where it's set up and you just have to recognize it. But let me just show you. It's still a proper tool. It's just not used as much anymore. The limit as x goes to -1 from the left of f of x minus f of -1 all over x minus -1, which is x plus 1. We'll analyze that, and then we'll do the same thing from the other side, f of x minus f of -1 all over x plus 1. So on the left side, we're going to use f of x from the left, which is the 2x minus 1. And then minus f of -1, when we plugged it in, we got -3, so it becomes plus 3 all over x plus 1. So if you simplify that, you're going to get 2x plus 2, which when you factor out is 2 times x plus 1 divided by x plus 1. That's the bad guy. It divides out, and there's nothing to plug in. You get 2. So once again, that's not surprising. Because the limit from the left was the same as the function value, and it's a line with the slope of 2, we get 2 there. Well, let's see what happens on the other side now. We get the limit as x goes to -1 from the right. The f of x that we use now from the right is 2x plus 1 minus -3, which is still plus 3. So again, that's the key. We use the same function value on both sides, all over x plus 1. If you try direct substitution here, you're going to get 2. You're going to get -2. You're going to get 4 minus 2. You get 2 over 0. What does 2 over 0 mean? Yeah, d/e, some type of infinity. So as soon as one of them doesn't exist, or any two of them don't equal each other, it's game over. And so I'll just say, so f of x is not diffable at x equals -1. And if you had to cite the reason, you would have to say, since the difference quotient from the right does not exist, okay? Maybe D and E is a better answer here. All right, so even though the slopes were the same on both sides, the alternate form catches it. All right? The last thing I want to talk about is the symmetric difference quotient. You don't have to worry about it, except know for the fact that it's important because your TI graphing calculators are programmed using this symmetric form. And I'm not going to do example 14 because the entire next section is all about using the calculator, and I'll show you why sometimes the calculator is wrong. But here's what the symmetric difference quotient is. Let's say I want to find the slope of the tangent line right there at C. What the symmetric difference quotient does is it chooses another point over here that's h units away. So that'd be C plus h. But then it goes back and uses another point that's h units away on the other side, C minus h. And notice that if you were just going to do a single calculation, that light blue secant line is a pretty good approximation of the tangent line. And so that's why they get this right here. The change in the y values, f of c plus h minus f of c minus h, all over the change in x, which you could clearly see here is 2 h's wide. If you let h still go to 0, you're letting this point converge to that one and this point converge to that one. You end up with the same result. But it's going to be a problem for the graphing calculator if you ask it to take the derivative, which we'll do that on Monday. If you ask the calculator to take the derivative at 0, it's using a symmetric difference quotient. So it's using this horizontal line, and it's saying the slope is 0 there, then it's coming in, the slope is 0, 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 the slope is 0. So guess what your calculator will tell you the slope is at the vertex? 0. When in fact we know it is D and E. Perfect timing. Have a productive day tomorrow working on your worksheet. We'll see y'all back on Monday. The worksheet's due on Tuesday.